Today I will talk about factors that affect the acid and base strength, and there are many important factors, but I will only mention inductive effect and substituted groups. And in this video I will not talk about the, for instance, solvation effects, so that all the base and acidity values will be valid for the gas phase reactions. Then I will explain the gas phase, base and acidity thermodynamically by using the proton affinity, so this one, and electron affinity concept. Then I will also mention about the formation of the adducts, and it is also related with the Drago equation. So we can, I think, begin. So the first effect that I want to mention is that inductive effect. So inductive effect. Inductive effect is important to bond strength between the acidic hydrogen and the other part of the molecule. And I want to give an example. The first example might be acetic acids. In the gas phase, it ionizes and creates proton or hydrogen plus. If we look at the molecular geometry of this molecule, we see that we have hydrogens, we have another carbon atom, we have an oxygen, and we have a proton. So here acidic hydrogen is this one. This is acidic hydrogen or acidic proton. So if you make this bond weaker, this molecule becomes a stronger acid. And how can we do that? The simplest way is adding electronegative atoms. For instance, we can add chlorine atoms. This molecule can ionize like the acetic acid. So in the molecular geometry, we are adding the chlorine atoms here. What's happening is that chlorine atoms is more electronegative than the hydrogen atoms. In this case, it takes the electrons to itself, and there will be a negative charge here, definitely due to the electronegativity of the chlorine atoms. So this bond becomes weaker. And weaker bond causes more acidic molecule. So if we look at the equilibrium constants, acidic equilibrium constants, acetic acid is around 10 to the minus 5, and the chlorinated form of this acid, K equilibrium, is bigger than actually 10 to the minus 3. So this molecule is definitely more acidic than the acetic acid. So this is more acidic. So if we look at the oxy acids, for instance, we have HOCl and we have HOClO. We are adding oxygen. Then if I add more oxygen, it becomes a stronger acid. So this is a stronger acid since there are so many oxygens, and this acidic proton can be released more easily when we add more electron drawing groups. The other thing here actually is the oxidation state. For instance, chlorine has +7 oxidation state, chlorine has +5 oxidation, chlorine has +3 oxidation state, and here chlorine +1 oxidation state. When electronegativity of the central atom increases, then it becomes more electronegative. When it makes more electronegative, then we will have more strong acid. And these kind of acids, pK, can be calculated 10.5 minus 5n minus x, and here n is the oxygen atoms except the OH group, oxygen atoms, and xn is the electronegativity value of the central atom. So this is the inductive effect plus the electronegativity value of the central atom. So there are two effects here, but inductive effect definitely explain the strength of these oxy acids. And substitution is another thing that affects the basicity. For instance, we can look at the basicity or acidity, and substituted amines are affected by the acidity strength. Again, we have, for instance, ammonia. This is the Lewis structure of ammonia. We have 2 electrons. These are the electrons that will be donated by the base, so NH3 here. But the electron density of the ammonia is affected by the substitutions. So, for instance, if we have a hydrogen, it's not a electron donating group, but it is also a poor electron donors. So ammonia electrons can be donated easily for this case. Again, we are talking about the gas phase. We can replace the hydrogens, for instance, with an electronegative atom. So in this case, we have a electron withdrawing group, right? Electrons will be taken by the fluorine atom. Since fluorine is very electronegative, I can put the electrons of the fluorine to make the Lewis dot structure correct. In this case, we have a partially plus charge on the nitrogen, and we have partially negative charge on the fluorine atoms. And fluorine atoms takes the electron density from the nitrogen, and these electrons cannot attack the, for instance, an acid easily, since these electron density were taken by the fluorine atoms. However, we have another kind of substitutes, for instance, alkyl groups. And alkyl groups, unlike the fluorine, they are good electron donors. Electron donor groups. So when we add the electron donor groups, we increases basicity. What's happening is that if we add the NH3, for instance, I will use this molecule, or we can just add a methyl group, right? So methyl group, CH3 group, can donate its electrons the opposite way. It is the opposite way of the fluorine. In this case, electron density of the nitrogen increases. And when electron density of the nitrogen increases, this part becomes more partially negative charge, and it attacks the acids easily. So it can donate its electrons. I want to talk about the little bit of thermodynamic concept. So firstly, I want to mention about gas phase basicity. In gas phase basicity, I can define a base as a gas phase, or this base has already a minus charge on it. So it can take a proton and it can become BH or BH plus. In gas phase. In this reaction, we can look at the proton affinity. Delta H of this reaction is definitely negative. However, proton affinities are always listed as positive numbers. This kind of reactions are very exothermic, and the proton affinity can show the base. High proton affinity means that the base increases. So high proton affinity again we can compare two bases, for instance NF3 and NH3. So I mentioned that NF3 is a weak base and NH3 is a stronger base due to the electronegative atoms on the fluorine. Fluorine takes electrons and the electron density of the nitrogen decreases, which decreases the base strength. And if we look at the reaction in the gas phase, always gas phase, proton affinity of this reaction is 604 kJ per mole, and the NH3 gas phase reaction is 872 kJ per mole. So these are definitely minus delta H values, but the proton affinity values are positive. I don't know why, but they use the positive values for the proton affinity. So red ones are the proton affinity. We can look at the gas phase acidities, and in this case we should look at the proton loss. For instance, we have HF, which is a weak acid, and it ionizes, gives a proton, and it causes the formation of fluorine minus ion in the gas phase. And these reactions are endothermic, and the delta H of this reaction 1554 kJ per mole. And if we look at the acetic acids, delta H is equal to and if we look at the CF3COH, So definitely we can say that this is the strongest acid, and this is the weak acid. So we looked at the Brønsted-Lowry type of acids and bases, and we can look at the gas phase reactions by using Lewis acid base cases. So what does it mean? Lewis bases is defined as the good electron donors, and the Lewis acids are the electron acceptors, as we mentioned. And the gas phase acidities, we can look at the electron affinity values. So larger electron affinity causes strong acids. And we can look at some Lewis acids. For instance, potassium takes an electron, it becomes a potassium, and electron affinity value is 419 kilojoule per mole. We can look at the calcium 2 plus. We can look at the manganese 2 plus. So in here, platinum 2 plus is the strongest acid since its electron affinity is higher than the others. I want to talk about the Drago equation. Drago equation is used to understand the schematics of the Lewis acid and base interactions. And the Drago equation is simply minus delta H equals to EA times EB plus CB times CA. CA times CB means that it is covalent interaction, and the EA and EB are the electronic interactions, and all these values tabulated. For instance, we have a pyridine and we have a acid-base reaction here, and pyridine plus O2 is our adduct formation. And we can calculate the enthalpy of this reaction by using the Drago equation. And the delta H for this reaction can be written EA times EB plus CB CA times CB. EA is 0.5 for acid, which is the iodine here. Iodine is the acid, and the pyridine is the base, since it's a electron donor, right? It can donate the electrons. And EB is 1.78, and CA is 2.0 times 3.54. So this reaction is 7.97 kilocalorie per mole. So it is around 33 0.3 kilojoule per mole. So we make a unit conversion. So it's a weak interaction, therefore I think it's called as the adduct formation. If you look at the bonds are generally stronger than the 200 kilojoule per mole at least. And we can make another example for the Drago equation. For instance, we have a CH3 N molecule. We have a toxic gas, SO2, and we have an adduct formation. So maybe I can write as SO2. So here it's a definitely base. It's a good electron donor. It donates the electrons to SO2 and creates an adduct. SO2 accepts the electron, so it's the acid. And this is our adduct. And we can calculate the delta H of this reaction. And theoretically calculated value is 38.5 kilojoule per mole, and also experimental delta H value of this reaction is 40.2 kilojoule per mole. So definitely there is a weak bond here. This is a weak bond.